was very challenging, and it had, I guess, unfortunately, it had a long history from the time we first thought about it until we started actually building things, and that period of time gave us some opportunity to go through some of the challenges together. And I think we realized that everybody brought some unique expertise to the table. The world's expert on X-ray telescopes was Leon van Spaebroek, who competed and was chosen to be the telescope scientist. He's unfortunately passed away, but he was with us for the first few years after Chandra launched, and he got to see the beautiful images that Chandra returned.
In addition to Leon van Spaebroek, many people contributed to the future telescope's success. Bruno Rossi, of course, and the invaluable leadership and vision of Nobel Prize winner Riccardo Giacconi.
Giacconi is an extraordinary leader, a scientific leader in particular, because he's an excellent scientist. He has the highest integrity and sense of what's important, and he inspires people.
He had enormous vision of where the field of X-ray astronomy was going to go and what was going to be useful.
What he didn't see, of course, were the answers, but he saw the questions. He saw that X-ray astronomy was going to be important. He saw that technically you needed X-ray telescopes. He saw that some of the most important questions were, how do galaxies evolve? How do clusters of galaxies evolve? And he saw the ways how you would go about answering those questions. The program was originally called the Advanced X-ray Astrophysics Facility, what a mouthful, or AXAF for short, which is sort of sounded pretty harsh. It was a facility so that it wouldn't be a telescope, because we were asking for something new, and we had already asked for the Hubble Space Telescope, so we didn't want to ask Congress for 2 telescopes. We were going to ask for a facility. And this was the name for many years. And then as we approached the launch, we held a contest. We ultimately chose the winner, the name Chandra, which was short for the last name of Nobel Prize-winning Indian-American astrophysicist Subramanian Chandrasekhar. And it was a very appropriate choice of name because he did a lot of work on astronomy and astrophysics, hence the current name Chandra. Very fitting.
With a superbly built observatory up and running and properly named, attention turned to the detection of X-rays. But what are the main processes which generate X-rays?
There are a number of different ways that X-rays are generated in the universe, and one of those ways is temperatures very high. To produce X-rays, you need a lot of energy, therefore you need a lot of heat, and we're talking about temperatures of millions of degrees. The hot skins of stars are like that. Another way is having charged particles move in magnetic fields. Very strong magnetic fields or very energetic charged particles, or both. And we have that situation, for example, in the vicinity of these compact objects called neutron stars, where we have huge magnetic fields. Those are 2 very principal mechanisms. Another way of adding energy, probably about the 3rd category, is gravity. Accelerate a charged particle really hard, and it will radiate X-rays. And if you just let it fall to the surface of a very compact object, neutron star, or in the vicinity of a black hole outside the event horizon so you still can see the X-rays, that's a way of producing X-rays.
The very first images began to give you a sense that Chandra was going to be very different. The official first light image of Cassiopeia A, in just about an hour and a half's exposure, we could see a faint dot in the center of the image, which is the neutron star that was formed when that star blew up 300 years ago.
We've seen this so clearly, how beautiful the Chandra images are. They're not only beautiful, they're spectacularly scientifically informative. One just has to look at, for example, the discovery of the ring around the Crab pulsar, where for the first time you see what people have theorized, that the wind of particles emanating from this pulsar would become shocked and start radiating in X-rays a distance from the object. And there's that ring, just like everybody thought it should be. And now you can study it in detail. From normal stars to comets to planets to active galaxies to supermassive black holes, to finding out that the hot gas in clusters of galaxies is not distributed nice and uniformly, that there's a lot of action going on, that those big active galaxies that are in clusters of galaxies and their supermassive black holes are doing all kinds of things on timescales of hundreds of millions of years. It sounds like a lot, certainly to me, but it's very short in the lifetime of a cluster.
We know that now in the centers of all galaxies that there's a supermassive black hole that has masses of up to a few billion solar masses. It's very compact, and at very early stages, these were very active, and they corresponded to the quasars that are seen at very high redshift. But these supermassive black holes that were, formed at very early stages of the universe didn't go away. So they're still sitting there at the centers of the galaxies. So when you drop a little bit of material onto them, they give off X-ray emission primarily. Sometimes a bit of radio, sometimes a bit of infrared, but a fair amount of X-ray emission comes off.
Clusters are another area that are very active, and again, this was a surprise. We discovered a lot of structure in clusters of galaxies, which in the X-rays we had thought were pretty smooth, because mostly what we see is hot gas, and most clusters are very, very big, and it was imagined that they were in equilibrium and fairly smooth. But in fact, they found lots of structures of sort of like cold fronts that you get in the weather on the Earth. And Chandra is the only satellite that will be able to resolve those as well.
In the X-rays, what we actually see are regions around these black holes and these galaxies and these clusters. We see regions where the gas is carved out or pushed away, and we call them voids. They may not be totally empty, but the density of the gas is down by a large factor. And in those regions where the X-rays are deficient, where the gas voids exist, is the same regions where you see the radio lobes, these jets and lobes that are formed from the radio. So you know that energetic particles are being shot away from the black hole by some kind of mysterious process, and they're clearing the gas away. They're pushing the gas aside. Because the gas has a density and a temperature properties that we measure in the X-rays, it's very easy to calculate the amount of work that's needed to clear these voids. So you can actually measure the energy that's carried out by these jets of particles. You can measure the energy release. It's almost like a fossil record.
Well, Chandra is no doubt going to go down in history as one of the major astronomical missions that took us from very sort of rough descriptions of how the cosmos works and start to build up detailed pictures of what's really happening. Envisaged in the sort of 1960s originally, it was preceded by other X-ray missions, but missions which couldn't look in such detail as Chandra can. So Chandra is now taking all those sort of very vague ideas that we had about the way the X-ray universe was working, and really giving us the physics behind it, rather than just sort of vague descriptions of how things might work. We're now starting to know how things work with Chandra. Chandra is essentially that link between the very vague, building up the physical understanding of what's really going on, and then going on from there to study things in much greater detail.
There's a very interesting Chandra result on a cluster of galaxies known as the Bullet Cluster. There's a small fragment of galaxies, a subcluster that's merging, and a shock has been formed, and it sort of looks like the edge of a bullet tearing through a fabric. We've seen that most of the mass is determined by the location of the X-ray emitting gas, and separately using Hubble and the Very Large Telescope and the Magellan Telescope on the ground, we've used a process called lensing to map the overall distribution of material by looking at the distortion and the shapes of galaxies on the far side of the cluster. Most of the material, namely the dark material, is located slightly in front of this X-ray gas that we see with Chandra.
Dark matter is important because most of the cluster mass, it turns out to be in the form of dark matter. So, and clusters are so big that the composition of clusters is exactly the same as that of the entire universe. So we can say if in these clusters of galaxies, dark matter makes 70% of the total mass, we can extrapolate this result on the entire universe. if dark matter in the cluster makes 70% of the mass, it makes 70% of the mass in the entire universe.
So the reason why this matter